Probability is the numerical measure of the chance that an event will occur. Its value always lies between 0 and 1. 0 means an impossible event, and 1 means a certain event. The probability of an event is calculated by dividing the number of favorable outcomes by the total number of equally likely outcomes. Some important properties are: the probability of the sample space is 1. The probability of an impossible event is 0. The probability of the complement of an event is 1 minus the probability of that event. Conditional probability is the probability of an event occurring when another event has already occurred. It is calculated by dividing the probability of both events occurring together by the probability of the given event. The main idea is that once the given event has happened, the sample space changes. Memory trick: given means divide by the given event. Next is Bayes' theorem. Bayes' theorem helps us calculate the reverse probability by updating our previous belief using new evidence. In simple words, posterior probability equals likelihood multiplied by prior probability divided by evidence. Here, prior means the initial probability. Likelihood means the probability of getting the evidence if the event is true. Evidence means the total probability of observing that evidence. Posterior means the updated probability after considering the evidence. Bayes' theorem is widely used in medical diagnosis, machine learning, spam filtering, and decision-making. Memory trick: posterior equals likelihood multiplied by prior, divided by evidence. Let's learn independent events. Two events are called independent if the occurrence of one event does not affect the probability of the other. To find the probability of both independent events occurring together, simply multiply their individual probabilities. Another important point is that even if one event has already occurred, the probability of the other event remains unchanged. For example, tossing a coin and rolling a die are independent because the result of one does not influence the other. Remember, independent events are different from mutually exclusive events. Independent events can happen together, but mutually exclusive events cannot. Memory trick: independent means multiply. A random variable is a function that assigns a numerical value to every outcome of a random experiment. It is usually denoted by the letter x. There are two types of random variables. A discrete random variable takes countable values, such as the outcome of rolling a dice or the number of heads obtained in coin tosses. A continuous random variable takes infinitely many values within an interval, such as height, weight, or temperature. For a discrete random variable, probabilities are represented using the probability mass function, or PMF. For a continuous random variable, probabilities are represented using the probability density function, or PDF. Next, distribution function. A distribution function gives the probability that a random variable is less than or equal to a particular value. It is written as f of x is equal to the probability of x less than or equal to x. The value of a distribution function always lies between 0 and 1. It is a non-decreasing function. The value of the distribution function at -infinity is 0, and at +infinity, it is 1. For continuous random variables, the probability density function is obtained by differentiating the distribution function. Expectation and moments. The expectation of a random variable represents its long-run average value. For a discrete random variable, the expectation is calculated by taking the summation of x multiplied by its probability. For a continuous random variable, the expectation is calculated by taking the integral of x multiplied by the probability density function. Moments describe the important characteristics of a probability distribution. The first moment represents the mean. The second moment represents the variance, which measures the spread of the data. The third moment represents skewness, which indicates the symmetry of the distribution. The fourth moment represents kurtosis, which describes the peakedness of the distribution. The moment-generating function is a mathematical function used to generate all the moments of a random variable. It is defined as mem of x of t is equal to the expectation of e raised to the power tx. For a discrete random variable, it is calculated by taking the summation of e raised to the power tx multiplied by the probability of x. For a continuous random variable, it is calculated by taking the integral of e raised to the power tx multiplied by the probability density function. Some important results are: the value of the moment-generating function at t equals 0 is 1. The moment-generating function is used to calculate moments, derive statistical properties, identify probability distributions. A univariate distribution describes the probability distribution of a single random variable. There are two main types of univariate distributions: discrete distributions and continuous distributions. Discrete distributions are used when the random variable takes countable values. Some common discrete distributions are Bernoulli, binomial, geometric, and Poisson distributions. A Bernoulli distribution has only two possible outcomes: success or failure. A binomial distribution describes the number of successes in a fixed number of independent trials. A geometric distribution gives the number of trials required to obtain the first success. A Poisson distribution is used to model the number of rare events occurring in a fixed interval of time or space. Continuous distributions are used when the random variable can take any value within an interval. Some common continuous distributions are uniform, exponential, normal, and gamma distributions.
Two random variables are said to be jointly distributed when their probabilities are described together. The joint distribution gives the probability of two random variables occurring simultaneously. The marginal distribution gives the probability distribution of a single random variable by summing or integrating over the other variable. The conditional distribution gives the probability of one random variable when the value of another random variable is already known. These concepts are widely used in probability theory, Bayesian statistics, and machine learning. Chebyshev's inequality provides a lower bound on the proportion of observations that lie within a specified number of standard deviations from the mean. It is valid for any probability distribution with a finite mean and variance. The inequality states that the probability of a value lying within k standard deviations from the mean is at least 1 minus 1 divided by k squared. For example, at least 75% of observations lie within 2 standard deviations, and at least 88.89% lie within 3 standard deviations. A sampling distribution is the probability distribution of a statistic obtained from all possible random samples of the same size. The most common sampling distribution is the sampling distribution of the sample mean. The expected value of the sample mean is equal to the population mean. The standard deviation of the sampling distribution is called the standard error, which decreases as the sample size increases. Sampling distributions are the basis for estimation, confidence intervals, and hypothesis testing. A transformation of a random variable means converting one random variable into another using a mathematical function. The transformation is commonly written as y equals g of x. The transformation changes the probability distribution of the original random variable. Transformations are used to simplify calculations and derive new probability distributions. The characteristic function uniquely describes the probability distribution of a random variable. It is defined as phi of t equals the expectation of e raised to the power I tx. The characteristic function always exists for every random variable. If two random variables have the same characteristic function, then they have the same probability distribution. Characteristic functions are widely used in probability theory and limit theorems. The modes of convergence describe how a sequence of random variables approaches a limiting random variable. The 4 important modes are Almost sur convergence, convergence in probability, convergence in distribution, and convergence in mean square. Among these, almost sure convergence is the strongest, while convergence in distribution is the weakest. These concepts are fundamental in asymptotic statistics and probability theory. The law of large numbers states that as the sample size increases, the sample mean gets closer to the population mean. The weak law of large numbers states that the sample mean converges to the population mean in probability. The strong law of large numbers states that the sample mean converges to the population mean almost. Surely, these laws explain why larger samples generally provide more accurate estimates. The central limit theorem, commonly known as the CLT, is one of the most important results in statistics. It states that as the sample size becomes large, The sampling distribution of the sample mean approaches a normal distribution, regardless of the original population distribution, for the central limit theorem to apply. The observations should be random and independent, and the sample size should generally be at least 30. The standardized statistic is calculated using z equals the sample mean minus the population mean, divided by the standard error. The central limit theorem forms the foundation of confidence intervals, hypothesis testing, and statistical inference.